let's talk about how we might solve a pedigree problem. So we'll focus on this one here. Okay, so a few important rules, right? Remember that males are going to be squares and females are going to be circles, right? So this is dad and this is mom here, connected by a horizontal line. And then the children are going to be vertical lines coming off of that. And you also want to remember that a filled in circle or a filled in square represents a person who is affected by the disease, okay? Now, if a trait is dominant, one parent must have it. If a trait is dominant, right? So if we look down here to the first generation of children, you can see we have an affected girl and an affected boy here. If we look up at the parents, we see dad is unaffected, but mom is affected. So already in my mind, I'm going, okay, so we have some affected kids and we have an affected mom. Now I'm thinking maybe we're dealing with a dominant disorder. So that's how you decide if something is going to be dominant or recessive, right? Look to see how often the disorder is appearing in each generation. The other thing you want to look for is you want to figure out whether or not you're dealing with an autosomal disorder or a sex-linked trait. So remember that your sex chromosomes, of course, are going to be X and Y, right? The things that make us male and female. Autosomes are everything else, right? Chromosomes 1 through 22 are going to be your autosomes. So autosomal disorders, you're going to be more likely to have an equal or roughly equal number of males and females affected by an autosomal disorder. Whereas with a sex-linked disorder, right, more commonly we're going to be dealing with males that are affected. And remember, that's because they only get one X, right? They have one X. So if they are a carrier on their X chromosome for a certain disease, they're going to express it, right? Whereas females are XX, they have two X's. So if one of their X's is affected but the other is not, then they won't express that disease phenotype, right? So looking at this, I can see we've got 1, 2, 3, 4 affected females and 1, 2, 3, 4 affected males. So now my brain is going, okay, I think this is autosomal, right? So now, because we've got an equal number of males and females that are affected, I'm thinking autosomal, and because we've got an affected mother who's producing some affected children, and again, in the next generation, right, we're seeing this happen again. We've got an affected dad, in this case, with 2 affected kids. I'm thinking it's a dominant disorder, right? Autosomal dominant. Now, how might we figure out what everybody's alleles are in this case? Well, if we think this is autosomal dominant, that means that if you are unaffected by the disease, your genotype can only be the recessive alleles. We'll call it A, we'll use A. So little a in this case. So dad has to be little a, right? Unaffected in this case. Mom is the question mark. We know she has at least one dominant allele. She's big A, right? Because she's affected. But mom could either be big A, or big A, little a, right? She could be homozygous dominant or heterozygous. Both of these genotypes is going to lead to the affected phenotype. So we want to figure out what mom is in this case, right? That's our question. What is mom in this case? And so the easiest way to do this is to do the Punnett squares to see if we can produce this type of ratio of children, right? So if I draw a Punnett square, and we'll go ahead and put dad on the side as little a, right? And mom on top, one big A at least. And why don't we go ahead and try the fully dominant situation first, where she's big A, right? And then we do this cross. What you'll see is that for all possible outcomes here for the offspring, all of the offspring would end up being heterozygotes, big A, little a, which means all of their offspring would be affected. They would all have at least one dominant allele. But we see that that's not the case, right? They did produce an unaffected daughter. So for that reason, we know mom can't be big A, right? This is wrong. So the other Punnett square we can do, obviously, is to cross our homozygous recessive dad, little a, with a heterozygous mom, big A, little a. And if we do that cross, we get big A, little a, another big A, little a, and another little a. So in this case, 50% of the time, our kids are going to be heterozygotes, big A, little a, and they're going to be affected. They're going to express the phenotype. And 50% of the time, our kids are going to be little a, or unaffected. And that matches what we're seeing here, right? We only have 3 kids, so we can't do the 50-50 thing, but 2 are affected and 1 is unaffected, right? So mom must be a heterozygote. She must be big A, little a. So now moving on to the next generation, obviously we know we have an unaffected daughter. She's got to be little a, just like dad. And we know based on our correct cross here that that's possible. We can get that. And based on this cross, we also know that the other 2 affected kids both have to be heterozygotes, right? So this one has to be big A, little a. This daughter has to be big A, little a, just based on what mom and dad's alleles are, right? So we know what those genotypes have to be in that case. So hopefully this is clear to everybody how we might go about figuring this out, figuring out mom's and dad's genotype and then that of their resulting kids. We won't go any farther in this case. I just wanted to use this to demonstrate to you how I might go about trying to figure one of these out. Always, always, always remember, draw your Punnett squares, right? If you're stuck between 2 different genotypes. So if, for example, you wanted to tackle this branch of the family next on your own, and you're trying to figure out what this husband's genotype is going to be, and you know, okay, he's affected, so he's got at least 1 dominant allele, but he could be big A, little a, or big A, draw the Punnett squares. Draw out the possibilities and see if you come up with the appropriate set of offspring to do this yourself.